So we've been covering rational functions, all the key features that go into rational functions, and how they all play a role in creating a visual display or like a graph of this rational function. So this is kind of a review, but a rational function is a function of the form f of x is equal to p of x over q of x, and p and q are nothing more than polynomial functions. So they're just regular equations. They just look like a fraction. They're set up with a numerator and a denominator. Each numerator and denominator has their own unique function, their own unique features. But because it is a function, because it is a fraction, your denominator, or whatever polynomial is in the bottom of your fraction, is never allowed to be 0. That would create something like 5 over 0, and we can't do that. So we want to make sure that, certain things have limits to them or restrictions on them, so that we can indeed make this a function and not just some thing that isn't going to exist. One of our most basic rational functions is our parent function, and that is f of x is equal to 1 over x, and that's this image right here. The reason we say it's one of our most basic is because you can see that it has a horizontal asymptote, and you can see that there's a vertical asymptote. There's these curves that happen in opposite directions and in opposite quadrants. So it kind of tells us how this rational function is going to behave. If we have an image, we can talk about in behavior, limit notation. So a rational function, one of the key things about a rational function, what makes it unique, is that all of those rational functions, because they take the form of a fraction, are going to have an asymptote. And an asymptote is nothing more than a line that your graph approaches. Some people say it's like an invisible line that you can't cross. So for example, if I look, my graph curves right here on that blue vertical asymptote. That's where we have that curvature, that split in our graph, that discontinuity. We have vertical asymptotes, and so for example, the one that I just did in blue, we would name that as x is equal to -3, because it's going to split right here on that vertical. It also splits right here along a horizontal asymptote called y equals 1. If we look, our function lives between these asymptotes. And so when we talk about it approaches an asymptote, it's going to get really close to each one of those. It creates like a box for it to live in. So one of the features of a rational function that's not necessarily a common one, but as we're moving into a greater understanding of key features and rational functions and all of those, is something referred to as a hole. A hole is a missing portion of your graph. So if I look at this graph here, I have a hole. Now, I have a function. The function continues on either side of that hole. But the way I explained it to my students was, you can have holes in your pants. If you have a pair of pants, there's a possibility you could have a hole. If you don't have a pair of pants, you can't have a hole. So in order for us to have this hole that we see in the graph, we first have to have a graph or a function that we can see. So holes are what we call removable discontinuity. Kind of shrink this down here. They are called removable discontinuity. The reason they're called removable is because when we look at the equation, we can see there's a factor in both the numerator and the denominator. And what mathematicians or math individuals will typically say is that these values cancel out. I like to say that they have a value of 1, but we can use the word cancel out. And so we're able to remove that factor from both the top and bottom of our function. Therefore, we call it removable. Because it creates a hole, there's a jump in my graph. That's why we call it discontinuity. So removable, discontinuity. And here we have that hole because that factor was x minus 2. And we have a hole there. That value is located at x is equal to 2. Later on, we're going to look at how do we find like the actual ordered pair without looking at a graph. So kind of a big review. Whenever we're dealing with rational functions, we want to first make sure that we are in factored form. You want to be able to find the x-intercepts. Those are also commonly referred to as zeros. So they have like two names, but they mean the same thing. We're going to look at how to identify a y-intercept. So a y-intercept occurs when x is equal to 0. So my ordered pair is always going to be something like this, 0, and then my y-intercept. Vertical asymptotes, these occur when you're finding the values of q. So vertical asymptotes happen in the bottom of your fraction, and horizontal asymptotes happen when we compare the numerator and the denominator. So if this is my rational function, my zeros are found up at the top. My vertical asymptotes are found at the bottom. My horizontal asymptote is when I compare the degree of the top and the bottom. So the degree is the highest exponent attached to some variable. When the degree of my numerator is larger than the degree of my denominator, I don't have a horizontal asymptote. I actually have a slant asymptote, which we will learn to derive in a couple of topics. When the denominator is less than, when the numerator is less than the denominator, in my classroom we call it bottom heavy. So the largest exponent's in the bottom of my fraction. That's going to automatically be a 0. So horizontal asymptote automatically is 0. She's bottom heavy, automatically is 0. When the two degrees in the numerator and the denominator match, so for example, x squared and 3x squared, 5x to the fourth, 2x to the fourth, all of those exponents are the same, then what we're looking at is a horizontal asymptote when you compare the coefficient of p to the coefficient of q. So for example, if I had something that said 5x to the fourth plus 3x minus 1 over 6x to the fourth plus 5, I'm going to come in and I'm going to start with looking at those exponents. I'm going to say, hey, those guys are the same. They're balanced. So now I can look at what are these leading coefficients attached to those variables. And that's going to create, so that little ratio right here is what creates your horizontal asymptote. We have the horizontal asymptotes, we have the vertical asymptotes, we have the zeros, the x-intercepts, the y-intercepts. We're able to go in and create a graph that we can then look at to help us determine end behavior, all kinds of things. So let's start with a couple examples. I have them so that they build on one another. We're going to start with a really basic example and then kind of move into a more complex. So I want to start with looking at my function. I first ask myself, are both of these fully factored, meaning I've broken them down into different quantities, using parentheses and things like that. I notice there's nothing I can do up top. There's nothing I can do in the bottom. This is already fully factored. So I can start by kind of picking any key feature I want. I do know that my numerator is allowed to be 0, but my denominator is not allowed to be 0. This allows me to find those zeros, or what is also known as your x-intercepts, and these let me find my vertical asymptotes. So I'm going to start with the numerator, and I'm going to say, if x plus 1 is in the numerator, and the numerator is permitted to be 0, if I solve for x, I have -1, which means I have an x-intercept when x is -1, y is 0. What that looks like on a graph is -1, 0 is right here. So my numerator determines where my x-intercepts are. My vertical asymptote comes from the denominator, which we said is never allowed to be 0. So if I add 5 to both sides, here is my vertical asymptote, or an invisible line my graph never crosses, or that my graph approaches. So what that looks like, or what that translates to on a graph, is over here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have what I'm going to draw it using a dashed line. Most textbooks or examples will have a dashed line here. Here is my vertical asymptote, meaning that my graph is going to get really close, but it's never actually going to be able to touch it. So right over here, vertical asymptote, I have one at x is 5, and I have an x-intercept at -1, 0. So kind of moving through some of these key features, I'm asked to find my y-intercept. So y-intercepts occur right here on the y-axis, and at that value, your x-coordinate will always be 0. So what that allows us to do is kind of evaluate our function and say, okay, well, what if my x was 0? Then everywhere I see an x, I put a 0. And kind of just number crunch it out. So I have a y-intercept at the ordered pair 0, -1, 5th. So when I go to graph it, it's going to graph somewhere right here on my y-axis. So domain, I do domain last, so I'm just going to kind of work my way down. Horizontal asymptote. So horizontal asymptote, if I look at my function, I'm going to find my greatest exponents, and that would be here and here. And even though I cannot see them, they are a 1. So if you can't see it, it's a 1. I notice that they are the same. So what I want to do is focus on those leading coefficients. What's happening right in front of that variable. I don't see anything. So we have these imaginary, or not imaginary, excuse me, invisible 1s. And so I'm looking at the ratio between 1x and 1x. 1 divided by 1 is simply 1. So I have a horizontal asymptote. So we had a 1 over 1, which is just 1. So when I go to graph it, I have a horizontal asymptote that behaves right here. And I've kind of got my graph now where I've got 4 corners of my graph, not necessarily quadrants, but like I have corner number 1 created by 2 asymptotes, corner number 2 created by 2 asymptotes, corner number 3 created by 2 asymptotes, and corner number 4 created by 2 asymptotes. When I look at my function, nothing divided out. So like there was nothing here that could divide out. So in terms of holes in your graph, we have no holes. I will take a look at what a hole looks like. So now when I go to put it all together, I have an x-intercept and a y-intercept that I know my graph is going to go through. And it's also going to approach the asymptote. So it's going to get really close to the asymptote. Something like that. And because we studied rational functions and we know that they behave in such a manner that they're in like opposite corners. So this one is in the lower left-hand corner of my asymptotes. So the other one, the other portion of this graph will be somewhere in the upper right-hand corner. So we can kind of create an image. We can then go back and look at domain. So domain is any breaks that occur. So moving left to right, I know I can start at, I can start at negative infinity, and I'm going to travel this direction all the way until I reach that asymptote. So that asymptote occurs at 5. We're going to jump over the number 5, and we're going to keep moving in this rightward direction for eternity. So from negative infinity to 5, union 5 to infinity. Some people might say all of x, pick any x you want, just don't pick the number 5. Both of these formats are saying the exact same thing. It just depends on preference. It just depends on if you have a lot of discontinuities, rather than creating, interval notations that have like 6 and 7 different pieces to them, someone might just list out all the values you can't use. So there's just 2 ways of representing the same information. So let's look at one that does involve a whole. So number 5. So I want to start by looking at the numerator. Is there anything that I can do? Can I break it down? Can I factor it? It is already in its most simplest form. So I'm going to wrap it up in parentheses just to tell my eyes I've already looked at that. I've already checked that. Now, in the denominator, I do have an x squared, which means I'm going to end up with 2 sets of parentheses because I have an exponent of 2. And I kind of look at what's going on here, and then I work backwards. I do have a leading coefficient of a 1. And so the only way to get 1x squared is to have 1x times 1x. That gives me 1x squared. I then look at the last number and I say, okay, it's a 6. There are a couple ways to get the number 6. I could multiply 1 times 6, or I could multiply 2 times 3. I eventually need to be able to make the number 5 by adding them up. So you're like, well, how do I know I have to add it? Because the first thing I see is a plus sign, then a 5. So I know I'm going to be adding 2 numbers together to get 5. Well, I can add 3 and 2, or 2 and 3. And because I'm adding them, the signs have to be the same. I'm looking for a negative 5. So negative 2 plus negative 3 makes a negative 5. Now I am in factored form. The reason we love factored form is because if I look at my factors individually, I can see, hey, look, there's the same quantity in the numerator as there is in the denominator, therefore they cancel out. This is where we create a whole. The reason we call it removable is because you took it out of the numerator and you took it out of the denominator. It still creates a discontinuity, a hole. There's a break in your graph. What we want to do is be able to figure out the y coordinate to that. So once I have removed my hole, the function I'm looking at is x minus 2. 1 over x minus 2. That's all that's left over. So when you have a hole, basically what we're going to do is we're just going to see what happens if I put that 3 in. I get 1 over 1. So when I look at my hole, when x is 3, the y value is 1. So when I come to look at my graph, right here, there will be a hole in that function at 3, 1. Then we start picking off, the different key features. So I know my numerator is allowed to be 0. My denominator is not allowed to be 0. So start with your x-intercepts first. The top of my fraction is allowed to be 0. The bottom of my fraction is not allowed to be 0. Well, let's look at this statement in the numerator. 1 is equal to 0. That is a false statement. 1 can never equal 0. So in terms of zeros or x-intercepts, if that statement is false, then we don't have any x-intercepts. Our function will never touch the x-axis. And that's okay. That's legal. You're allowed to do that. Look at our denominator. So when x minus 2 cannot be 0, if I add 2 to both sides, then I know that I have to avoid using the value 2 because that's going to create a vertical asymptote. If I put a 2 in here, 2 minus 2 is 0. That's going to create for us a problem. So I have a vertical asymptote at x is equal to 2. Let's come right over here, Here's my vertical asymptote. Domain is last, so let's look at that y-intercept. So remember, a y-intercept is saying what happens if I replace all my x's with 0? Well, 1, 0 minus 2 is -2. So my y-intercept will say when x is 0, y is -1/2. So somewhere like right in here. And my last key feature is my horizontal asymptote, which is a comparison of my numerator and my denominator. Okay. So I'm only looking at like what's left over, not the original, because we knew that there were some things that we were able to eliminate out of this. Okay, so I'm looking at what's left over, and I'm going to compare my degrees. So I'm looking here, there is no x, so this is a 0. There's nothing there. This x has a 1. So when I compare these two, I say, well, she's bottom heavy. Like the x value in the bottom, the exponent is larger than the one in the top. And so since she's bottom heavy, she automatically has a horizontal asymptote at y is equal to 0. And that's automatic. So if she's got more degrees in the denominator than she has in the numerator, automatically y equals 0. So I've got these 4 corners to my graph. Now we can see here's one corner, falls between my asymptotes, falls between my asymptotes, and the 4th corner. My graph cannot have a hole if it doesn't first have a pair of genes. So it's got to have a function, that part of my graph that's running through it. And then there's my y-intercept, and I know that my graph will go through my y-intercept. And so here's my function. This allows me to create a visual for my domain. So my domain is going to start at -infinity, and we're going to move this direction all the way until we hit the first discontinuity, which is my asymptote. So we make it past the asymptote, and there's a little bit of space before we hit a hole. So we're going, if I'm going to zoom in really big here, we're coming over here, we hit this asymptote, right? We jump over the asymptote and keep going. And then all of a sudden we hit this hole. We have to jump over the hole and then keep going. So the hole happened when x was 3. So we're going to jump jump over the 3 and keep going forever. Again, some people may write it, pick any x you want to, just do not pick the following x values. It's a little bit shorter. New, it's new, so some people really don't like it because it's new, and that's totally okay. Number 6, in class we just focused on here because I wanted to focus on something called a GCF, also known as greatest common factor. It's what they have in common at the exact same time. So my numerator's done, it's factored. But I have x cubed minus x squared. And so this is x times x times x minus x times x. So my exponents tell me how many times that letter shows up. Exponent of 3, 3 different times. Exponent of 2, 2 different times. A greatest common factor says, well, what do they share in both terms at the exact same time? Well, they both have an x, and they both have another x. So when I factor it, I say they both have x squared, and they did not have, like in this first one, there is an x left over, and over here there's nothing, and we fill in nothings with a 1. So if I wanted to factor this, this would become x squared times x minus 1, And I can start to see, oh, look, there's a hole. There's a bunch of other things. I can start running my key features from there. I saved number 8 for last because it is pretty gnarly in that it is a lot of factoring. I'm going to start with the denominator simply because this is a 1, which means that in order to get a 1, I just have to multiply by 1x and 1x. I look at my 4. I say, okay, what are all the combinations to get a 4? That's it. When I read it backwards, I say, what combinations are going to have a difference, so something minus something else, and they have to make -3. So if I look, I can see that 1 and 4 make -3. I just got to figure out what order to put them in. If I put them in 4 minus 1, I get a +3. But if I do 1 minus 4, I get the -3 that I need. So I know that this is going to be a +1 and a -4. Up in the numerator, we have a lot more going on. Like a lot. So we have to factor that one. There are a couple ways to do it. I prefer factor by grouping, but I can also roll with like a guess and check. I will say, okay, it starts with a 3 and it starts with an 8. So if I put the 3 and the 8 together, I get a value of 24. And I'm going to come up with every combination I can to get 24. Because I know that my coefficients play a role in things, so I don't want to just throw this guy away. He plays a part in, if I'm putting it all together, he's going to play a role in making those numbers look larger or smaller when you do the multiplication. I need a combination that when I add those up, I'm going to end up with a -14. So two numbers that when I add them give me -14. Well, I know that 2 and 12 give me +14. -2 and -12 give me -14. So when I go to factor this, I'm going to actually rewrite this and change the -14 into a -2 and a -12. I have not changed its value. If we look, that's still -14x. I just changed what it looked like. The reason I do that is because I now have 4 terms. 4 terms allows me to work with 2 at a time. So let's just look at the first 2. If I look at 3x squared and 2x, they both share an x. If I took the x away from both of them, I would end up with 3x minus 2. It's like a form of division. Like you're dividing out your greatest common factor. On the other side, when I do this, it starts -12, so I'm going to keep my negative, and I'm going to look at what does 12 and 8 have in common. Well, they both share the number 4. So if I took -12 and I divided by -4, I would end up with 3x. If I take 8 and I divide out my GCF, I end up with a -2. The reason I love this method is because it is self-checking. Notice that you have the exact same factor that's left behind in your parentheses. So when you go to factor, when you go to put it in factored form, you can say the twins or the matching pieces. Take one set of one factor, and the GCFs that you used make the other one. And so now we're in factored form, and we can run those key features again. I can say, look, these guys are the same, therefore they cancel out. So I have a whole. When x is 4. Once I take out my whole, all I'm left at looking at is 3x minus 2 and x plus 1. So if I took out a 4, and I evaluated it, that's 12 minus 2 is 10. 4 plus 1 is 5. This fraction, 10 over 5, is just the value 2. So when I take out my whole, even though the x value is 4, the y value is 2. Looking at these, this is allowed to be 0. So if I look for my x-intercepts, I add 2 to both sides. I get 3x is equal to 2. Divide both sides by 3. I have an x-intercept at 2/3, 0. I also know my denominator is never allowed to be the number 0. So if I look in my denominator and it's never allowed to be 0 and I minus 1, I have a vertical asymptote at -1. So over here, there's this invisible line that happens right here at x equals -1 that we will never be able to cross. We're going to get really, really close to it, but we're never going to cross it. I have a hole at 4, 2. 1, 2, 3, 4, 2. I have an x-intercept at 2/3, so somewhere in here. My y-intercept, so my y-intercept occurs when x is 0. So if I come in here and I say, let me just put in a 0 everywhere. Okay, that's -2, and 0 plus 1 is 1, so -2 divided by 1 is just -2. Okay, that happened with 3 times 0 minus 2 over 0 plus 1. That's where that -2 came from. So I have a y-intercept at 0, -2. And all I'm left with trying to find, not my range, I have to find my horizontal asymptote. So I take a look at the top x and the bottom. I say, oh, the exponent is 1 on both of them. So I only have to compare these numbers. 3 over 1 is just 3. So I have a horizontal asymptote that is occurring here. And I can start to see there's like a curvature happening in the lower right hand corner. So I'm just going to follow that curve, jump over my hole. If it happened in the lower right hand corner, it also happened in the upper left hand corner. And so for my domain, I went from -infinity all the way up to my asymptote. Jumped over my asymptote, went all the way to our hole. Jumped over the hole and kept going forever. Or again, some people might say, any x that you want to choose, just please don't pick the following. Don't pick -1 and don't pick 4. So that's kind of looking at how all of these key features play a role in what we're doing, the interconnectedness of everything. Everything's, all the pieces work together to create graphs. All the graphs work together to give us information. So we're looking at just how are we exploring this and how can we take this deeper, create a deeper understanding.